Hi, hello. Hope everyone is well. So this is going to be the last sort of recording of the semester. So we'll get started, but thought it was worth noting. Okay, so here we are. Last time we finished up with exercise 3.38, so that leaves us with 3.39. 3.39 is telling us that there are different ways that you can view an equivalence, and in particular, what happens with an equivalence is that if two things are equivalent with respect to some relation, then the two equivalence classes are the same, and in addition, they don't have any overlap. That if you have two distinct equivalence classes, then they have no overlap. Okay, let me bring up the answers. So just to go briefly through it here, when we've seen a couple of proving of the statement where you say the following are equivalent, TFAE. The following are equivalent, and in this case there are three different parts: part 1, part 2, part 3. So the most straightforward thing to do here is to show that part 1 implies part 2, and then part 2 implies part 3, and then go on to show that part 3 implies part 1, and that'll mean that they all imply each other. This also breaks the job of what may look like a very big job into three smaller jobs. Show that if part 1 is true, then part 2 is true. Show that if part 2 is true, then part 3 is true. And finally, show that if part 3 is true, then part 1 is true. And so a person can say, well, I didn't get the third one, but I got the first two, kind of stuff. So you have some sense that it breaks a bigger job up into potentially into smaller jobs, and of course that's usually good. Okay, so the first part is to assume that the first statement holds, so that x naught is equivalent to x1 with respect to this relation. Okay, then the equivalence classes, the square brackets x naught and the square brackets x1, the equivalence classes are sets. So in order to show that the two are equal, the most straightforward thing to do is to show mutual containment. Show that x naught is square brackets x naught is a subset of square brackets x1, and square brackets x1 is a subset of square brackets x naught. And again, the right way to think of this is, for example, based on the prior homework, is you think of the regular integers broken up into different categories, equivalence classes, broken up into different categories according to what remainder they leave when you divide by 3. So there's a category, a class, a set, a collection of numbers that leave a remainder of 0 on division by 3. There's an equivalence class of sets that, of numbers that leave a remainder of 1 when divided by 3, and there's an equivalence class of numbers that leave a remainder of 2 when divided by 3. So that's 3 different equivalence classes. Just to pick on one, how about we pick on the numbers that leave a remainder of 1 on division by 3? You can write that as square brackets 1. It's also correct to write it as square brackets 4, because 4 leaves a remainder of 3. Also correct to write it as square brackets 7, because 7 leaves a remainder of 1 on division by 3. Square brackets 10, because 10 leaves a remainder of 1 on division by 3, and like that. Okay. So we're asked to show that if two numbers are equivalent with respect to this relation, and in the example that I was saying out loud there a minute ago, that means they both leave a remainder of 1 on division by 3. So if two things are equivalent with respect to this relation, then the equivalence classes are the same. And so, for example, the collection of things that are like 1 in that they leave the same remainder on division by 3 is exactly the same as the collection of things that are like 4 in that they leave the same remainder on division by 3. Okay, so we got to show that these two sets are equal, and we have some experience with showing that sets are the same by mutual containment. You assume that something is an element of the first, and then you go on to show that it's an element of the second, and likewise. Okay, so here we go. If a y is an element of the first, and shooting for y is an element of the second down here. So if y is an element of the first, then by definition of equivalence class, y is equivalent to x naught. So again, by definition of what equivalent to x naught with respect to the relation means, the pair y comma x naught is an element of R. And again, if you're saying to yourself, I want this touchstone example, so you're thinking that square brackets x naught, we'll call that square brackets 1. So if a number is in the class square brackets 1, if a number leaves the same remainder on division by 3 as 1, then that number is equivalent to 1 mod r modulo 3. Good. So so y comma 1 is an element of the relation, sort of stuff. And so you can kind of make sure that you're not going crazy by keeping kind of a prototypical example here. Okay, anyway, so now because x naught comma x1 is an element of the relation, after all, we assumed that x naught and x1 are related. So because x naught comma x1 is an element of the relation, transitivity, y comma x naught followed by x naught comma x1, transitivity gives y comma x1. So that means y is in square brackets x1. So sometimes having this mental picture of what's happening with respect to an example or two is useful for finding your way through a new abstract circumstance. I mean, it's true that after a while, after you've found your way through it a bunch of times, you start dropping the examples and you're just sort of able to proceed sure-footed. But it helps to have a couple of examples in mind. And containment in the other direction is similar, and so 1 implies 2. 2 implies 3 is very straightforward because both sets contain x naught. So I got to remind you what 2 and 3 are. If I can work my windows here. There we go. No, go away. There we go. Okay. So so 2 is 2 is that, here we go. 2 is that square brackets x naught equals square brackets x1, and 3 is that square brackets x naught and square brackets x1 have no overlap. Okay, so it says, back to the screen, there we go. It says that 2 implies 3 because both sets contain x naught. So if square brackets x naught equals square brackets x1, then both of those, the set which we're calling square brackets x naught, and also the set which we're calling square brackets x1, both of those contain x naught. And so square brackets x naught and square brackets x1 intersection is not empty because they have the same element, namely x naught. And then finally, for 3 implies 1. So you assume, statement 3, assume that the two equivalence classes of x naught and the equivalence class of x1 is not empty. So that leaves you able to take y as an element of that. And we aim to show here that x naught is equivalent to x1 modulo r. Okay, so then y comma x naught is in R and y comma x1 is in R because it's in both equivalence classes. Y is in both equivalence classes, so I can say that y is related to x naught and also y is related to x1. By symmetry, you get from y comma x naught to x naught comma y. Symmetry is one of the properties of capital R. It's because it's an equivalence relation. And then I'm obviously going to apply transitivity. I have x naught y and also y x1, so I have the two y's, the y on the right and the y on the left. Transitivity gives x naught comma x1, and so x naught is related to x1, and that's what I needed. Okay, so again, a person can find these abstract at first, absolutely find them abstract at first, but a little bit of kind of there's 3 things, transitivity, symmetry, and reflexivity. We must need to apply one of the 3 can go some way toward helping a person find their way around. Okay, let me pop this down again. I have too many things going on here. There we go. Okay, pop that down again. And so so we just did 39, and now I want to talk about the property that is kind of the mirror of equivalence classes. So what the equivalence classes do is they split the universe of things up into discrete chunks. And again, the natural example there is you take division by 3 and you look at the remainders. Some numbers have a remainder of 0, some numbers have a remainder of 1, some numbers have a remainder of 2. So in some sense, that's a goal of mathematics, is to break the universe up into the different cases that can happen. Those different cases that can happen is called, each one of them is a part, and the whole thing is called a partition. So of course I have to prove that the equivalence classes, etc. But first I got to define what I mean by partition. Okay, so there we go. Okay, so a partition of a set is a collection of non-empty parts. We're going to eventually think of those parts as equivalence classes. So a partition of a set is a collection of non-empty parts. It says P sub I is a subset or equal to capital X. So that every element little x in capital X is in exactly one of the P sub I's. Not 0 of them, not 2 of them, one of them. That is, each pi in the partition is non-empty, and the partition covers x. See that script p? Script p covers x. That is to say, the union of all the pi's is x, and the parts are pairwise disjoint. So, for example, in this picture, p0 and p1 don't have any overlap. p0 and p3 don't have any overlap like that. So pi and pj don't have any overlap unless they're actually the same. Okay, so I drew a picture there of a set, the usual bean diagram for a set, partitioned into four subset parts. So a person might think this is all the integers, and these are the integers which leave a remainder of 0 on division by 4. These are the integers which leave a remainder of 1 on division by 4. These are the integers which leave a remainder 2 on division by 4. And these are the integers which leave a remainder 3 on division by 4. You won't go wrong thinking of them that way. That I've taken a universe of things and divided it up into all the possibilities that can happen. Okay, and of course then, went too far. Of course then we have an exercise working with the three different concrete examples. I'm going to ask you to do part B because part B is related to the part B you did on the prior homework. Matter of fact, it's pretty much exactly the same as the part B you did on the prior homework, and I'm going to talk through part A and part C because they are related to the things that I did in 3.38. Okay. So it says verify that script P is a partition. So of course I'm going to have to go through the parts, go through the requirements in the definition. Verify that script P is a partition, and then it says how many parts does it have. So I'm going to have to somehow understand how it divides the universe up into the different pieces. So A. So the x is all natural numbers. So this bean is supposed to be all natural numbers. Inside the bean is every natural number, 0, 1, 2, 3, etc. And script P, it consists of two things, P0 and P1. So figuring out how many parts it has is not going to be too hard. Script P is two things, P0 and P1. So instead of the four-thing picture, it's just two things. Imagine split right down the middle. Where P0 is a set of even numbers and P1 is a set of odd numbers. So I'm going to have to show that that's a partition. I don't have to actually count how many parts because it's already right there. Okay, so in order to show it's a partition, I have to show that each pi is non-empty, that the union of all the pi's makes up, in this case, the natural numbers, and that the parts are pairwise disjoint. That if you take P0 and intersect with P1, you'll get an empty set. Okay, so let me pop up the video thing here. Let me see. There we go. Okay, so I have to show this is for 3.41a. Okay, so the lighting is a little weird. I don't know why the camera does that. Okay, so we have that script P consists of two separate things. That's supposed to be a capital P0, and that's supposed to be a capital P1. P0 is the set of evens, and P1 is the set of odds. So it's just simply supposed to be 0, 2, 4, etc. That's all. And P1 is 1, 3, 5, etc. And I have to show three things. I have to show that I have to show three things that each pi is not empty. I have to show that the union of the pi's is all of the naturals, and I have to show that if they are not equal, then they have zero overlap. So we must show three things. So first, P0 and P1 are both non-empty. I mean, come on, nobody in the class needs to be convinced of that. So first, P0 and P1 are each non-empty. Okay, and nobody in the room needs to be convinced of that. All right, second, that I got to show that the union of all the PIs, there's only two of them, but I got to show that the union of all the PIs, it makes for all of the natural numbers. We show that script P covers X, meaning that the union of the two PIs is X. Okay, but of course that's clear. And actually, we had results early in the semester that said a number is either even or odd, but it you know, again, the audience in this case is the folks in the class, and everybody in the class knows that exhausts the natural numbers, the evens and the odds. And then the third thing, pardon me, the third thing that we want to show is that the two don't overlap, that is to say they are disjoint. We show the parts are disjoint. And again, I'm not going to show anything because nobody in the room needs convincing of that. Is the empty set. That no number is both even and odd. I like that, and I'm going to write it down. And again, we certainly have results from the beginning of the book that a person can point to and say this follows from 1.2.3 or whatever the heck it is. But at this point in the semester, I hope that we don't need to, hope that I don't need to convince you that that a person can rely on those statements. Excuse me. Okay, so that was 3.41a. I'm going to ask you to. There we go. I'm going to ask you to pop up. I'm going to ask you to do 3.41b for homework because it's related to the homework that you just did. And then the last one that I want to talk about is 3.41c. So let me. Too many windows. Come on, go away. There we go. Went away. Okay, so 3.41c. Getting toward the end of the semester. 3.41c. And now I got to go back to the window and write down. So make sure I get the letters right. Okay, so script P is the set of all capital PX where X is a real, and specifically it's a PX is capital PX, darn it, capital PX is the set of y's that have the same sort of decimal expansion as x. It's a set of y's where x minus y is an integer. So for example, if x is 1.23, then y could be 5.23 or 9.23, sort of stuff, 0.23. Okay, so I have to show that the collection of PX's satisfies the three properties. First of all, each PX is non-empty. Second of all, if you take the union of all the PX's, you get all the reals. And third, that the PX's are, if they overlap at all, then they're the same. Okay, so let's try it. So we first show to see that each P sub x is non-empty. Note that x is in Px. Every number has the same decimal expansion as itself. To see that the union of all the px's it is the real numbers, equals the real numbers, comma. Just note here also that x, that reflexivity, x is in px. So every real number x is in the union. Is an element of the union. Oh, darn it. Sorry. The union x in the reals of px. Okay, and then the last thing, I want to show that that the only time the px's overlap is when they're equal. So the wrong thing to do, the mistake that a person can make here, is to say something like, let x be unequal to y, and then try to show px is unequal to py. The reason that's a mistake is because suppose x is 1.23 and y is 2.23. X is unequal to y, but px and py are the same. So instead, what you want to do is you want to, oh darn this stupid thing, there we go, is that you want to take advantage of this if-then statement. If pi intersect pj is not empty, then pi equals pj. That's the convenient way to show pairwise disjoint. The mistake is to try to say, assume x is unequal to y. The right way to show, the convenient way to show, is with this if-then statement. If pi intersect pj is not empty, then pi equals pj. That's the most convenient statement of pairwise disjoint. So now I gotta get rid of the speaking of convenience and inconvenience. There we go. So for the third, assume pi intersect pj is not empty. And then I'll leave a blank space, and down here at the bottom I'm thinking that I'm going to show then pi equals pj. Okay. So I assume pi intersect pj is not empty, and then down at the bottom here I'm going to say then pi equals pj. Now pi and pj are sets. In this case they're sets of real numbers. So to show that the two are equal, that's where I'm headed. To show that the two are equal, the simplest thing to do is to show mutual containment. So I'm going to say, if something is an element of pi, then, and there'll be some conclusion, then it's an element of pj, etc. Okay, so we show this by mutual containment. I hope that a person is getting a sense that that there's a strategy here, and that when you see, for example, showing that two things are equal sets, that then you say to yourself, I'll try mutual containment. That it has proven to be so convenient in the past that reaching for something else is not ridiculous, but perhaps a little bit perverse. So I'll assume that x is an element of pi, and I'll come to the conclusion that x is therefore an element of pj, and then likewise you can assume y is an element of pj and go on to show that y is an element of pi, and then that will show mutual containment and we'll be done. Okay, so suppose x is an element of pi. Okay, then by definition of pi, that means that x minus I is an integer. Okay, so I know that x minus I is an integer, and then the only other thing I need to know is I need to have something that gets me from pi to pj. But up here I have the assumption that pi intersect pj is not empty, so there must be an element in there. Because pi minus, intersect pj is not empty, it has a member oh, let's say y. All we know about y is that y minus I and y minus j are both integers. Okay, and then in order to show that x is an element of Pj, I have to show that x minus j is an integer. So is there some way I can get from these three, x minus I, y minus I, and x minus j, all of them integers, is there some way I can get to x minus j? So I guess it seems to me I can go from x minus I over to y minus I, and from there over to y minus j. So I guess it seems to me I get x minus I, then take away y minus I, and add y minus j. So consider. Enough room on the thing? Yes, enough room on the thing. X minus I, take away y minus I, add y minus j. Clearly it's an integer because it's adding and subtracting integers. But when you do the cancellation, x minus I, that's x minus I minus y plus I plus y minus j. And I think, if I did it right, I think that's x minus j. So minus I cancels with the plus I, minus y, I think that's x minus j. Is an integer. So x is in Pj. I think the argument that I think so Pi is a subset of Pj. And containment in the other direction is exactly the same. Containment in the other direction is similar. Okay? So again, just trying to step back here, getting near the end of the course, trying to step back here, is that we're asked to show that that this forms a partition, and showing that it forms a partition is three requirements. Two of the requirements prove to be not very hard. Once I got them written down. Two of the requirements prove to be not very hard, and for the third, there's kind of a strategy. A person thinks, well, we were given a certain if-then statement, and so I'm going to demonstrate the if-then statement. And furthermore, I have to show mutual containment. So I'm assuming x is an element of the first, and eventually going on to conclude that x is an element of the second. A person could absolutely look at this and say, I'm not sure I would have thought of that. Fair. You know, sometimes you're doing a problem and you just don't see how to do it. That's perfectly fair. It's happened to me thousands of times. That's perfectly fair. But it so happens that I thought integer, integer, integer and made it work. Really, I took out a piece of paper and penciled around until I get x minus j by fiddling with the parts I had. Okay? Okay. Okay, so it's a matter sometimes of taking out, being willing to take out a piece of paper and kind of fiddle with it and see if you can get it to go. Okay, let's see, that's 3.41, and then the other two things that I need to do is 3.42 and 3.43. So I'm going to ask you for homework to do 3.42b. So I'm doing 3.42a, and I'm going to, so 3.42a says where r is 3.42b, that's right. So where r is an equivalence on the set X, the collection of equivalence classes forms a partition. That is to say, the example I used above here where I said, what's the remainder on division by 4 would give you 4 different parts is right. When I was speaking informally then, and now this is the formal statement of what of what I said earlier, that if you have an equivalence relation, then you look at the equivalence classes, they split the universe up into the cases of things that can happen. Okay, so that's a little less surprising perhaps than some of the things we've seen before. So let's go to 3.43. Where'd you go? Where'd you go? Come to Papa. There we go. 3.43, and I'll pop it up. There we go. And I have that right? I do have it right. Okay. So 3.43a says where R is an equivalence relation, the collection of equivalence classes forms a partition of X, and this is the partition induced by the relation. So just the relation, I got to show it's reflexive, I got to show it's symmetric, and I got to show it's transitive. Okay. So it's reflexive simply because that's simply not the right place. There we go. That's better. Okay, so here, it says 3.42. So it says where R is an equivalence relation, the collection of equivalence classes forms a partition. So I have to show the properties of partition. So I have to show that no equivalence class is empty. That if that the collection of equivalence classes covers the underlying set, and then finally I have to show that equivalence classes are pairwise disjoint, and then that's just a question of working through the parts that we basically saw already. So X is an element of square brackets X of the equivalence class containing X by reflexivity. Reflexivity says that X comma X is always related to X. X comma X is in the relation capital R. So no equivalence class is empty. And likewise, for the same reason, every X is an element of some equivalence class. So those two are easy. Okay, and then obviously the part that requires some doing here is to finish, we have to verify that the equivalence classes are pairwise disjoint. And we're going to show that in the way that I showed the last example, that if two of them have a non-empty intersection, if two of them have a non-empty intersection, oh darn this thing, there we go. If two of them have a non-empty intersection, then they must be equal. And it's a somewhat odd way to phrase what I'm trying to phrase, but it proves to be very convenient, as I described in the last example. Okay, so suppose that the two of them have a non-empty intersection. I suppose that Z is an element of square brackets X intersect square brackets Y. That is, Z is an element of the equivalence class containing X and also an element of the equivalence class containing Y. Then I have to come down to the conclusion that So I'm trying to show that if the classes are not disjoint, then the classes are equal. So I'm trying to show mutual containment. So I suppose that Z is an element of the intersection, and I'm going to want to show that that square brackets X is a subset of square brackets Y. I'm also going to show that square brackets Y is a subset of square brackets X. Okay, so I had a little trouble getting it out. So suppose that Z is an element of the intersection, then Z is congruent to X mod Y, and Z is congruent to Y. Z is congruent to X mod R, and Z is congruent to Y mod R. To show that the two sets are equal, we want to show mutual conclusion, so we suppose that A is an element of square brackets X. And a person has this sense of in order to do this, you often do so. In order to do this, you often do so. And so that's, in order to show mutual inclusion, you often suppose that A is an element of the first and go on to show that A is an element of the second. Okay, so I have to use the information that I have so far in order to show that A is an element of square brackets Y, and I spot it down there. So, if A is an element of square brackets X, then A is equivalent to X mod R. Because Z is equivalent to X and also Z is equivalent to Y, you know, so we're able to get that we're able to swing from A to X to Z to Y. So here we go. You apply transitivity to get A is equivalent to X. X is equivalent to Z. Therefore, A is equivalent to Z. And finally, Z is equivalent to Y. So that gives me that A is equivalent to Y, because this is transitive. A, Z, Z, Y. So I swung from A to X to Z to Y. And so A is an element of square brackets Y. Containment in the other direction, of course, works exactly the same way. So to show that something is a partition, you need to show three separate things. And the first two, not a rule that they have to be obvious, but the first two are often very easy. To show that no element of the partition, no part is empty, and then finally that every element of the underlying set, every element of capital X here, every element is in some part. Those two are typically easy, typically reflexivity. And then the third part, you use this, there we go. The third part, you use this property of you've got to show the pairwise disjoint, and you use this somewhat peculiar way of phrasing pairwise disjoint. Turns out to be the convenient way to show, often the convenient way to show that pairwise disjoint. So you assume Pi intersect Pj is not empty, and you go on to show that Pi equals Pj, and often you go on to show that by mutual containment. Okay? Okay, so I'm going to ask you to do B, so I'm not going to do B right now. And then the last thing I want to do is to show here. There we go. The last thing I want to do is to show the part that I popped up a little earlier prematurely by accident. There it is now. Okay, so I'm on 3.43, and I want to show, suppose that you have a function f from a domain to a codomain, and I want to show that the relation d1 d0 comma d1, where f of d0 equals f of d1, is an equivalence on D, and that the set of inverse images partitions the domain. And then I'm going to show this. I'm actually going to do here just an example. So if I can manage to undo that, there we go, undo that window. So I'm going to talk about this this particular equivalence relation. So this is 3.43, and it's a sketch of the three parts. Okay. So I want to consider just two examples. The first is f mapping the reals to the reals, given by x goes to x squared. The familiar calculus example of x goes to x squared. And now we have the reals to the reals. Okay, and we know, everybody knows, that 2 maps to the same place as minus 2. Okay, so that is to say, when I start at 4 and pull back to the domain, I end up with a set of size 2. Oops, got a little sideways there. F inverse of 4 is a set of size 2. F inverse of 9, I know you know this, is a set of size 2. F inverse of 2 is a set of size 2. The only exception is that F inverse of 0 is a set, it turns out, only of size 1. This splits the reals up into infinitely many parts, each, with one exception, of size 2. So we can define P sub y to be the set of x's where x squared equals y. And the py form, that's a p, not a very good looking p. That's the py form a partition of the domain. Okay, and it's nothing that you don't know already. It's just a different language to express what you knew already. And you might say, for example, that square brackets 2 is the same thing as square brackets minus 2, and both of them could be called p sub 4. And they just consist of 2 and minus 2. And likewise, square brackets 9 and square brackets, square brackets 3 and square brackets minus 3 are the set that we could call p sub 9, and it just consists of 3 and minus 3. Okay, so that for any function, this is only one example here. X goes to x squared. I'm going to do another example in just a second. But for any function, the pullback, that is taking the inverse image, partitions the domain into these sets. In this case, the sets all have 2 elements except for a single set that has 1 element. A person might notice that that these are all the folks who go to 4, so this has something to do with one-to-one functions. If these inverse images are all of size 1, if the elements of the partition, if the parts are all of size 1, then you have a one-to-one function. If any element of the partition, if any of these parts has more than one thing in it, why then you don't have a one-to-one function. Okay, it's the other example, and again, it's something that you already know, but just to bring this into contact with a familiar case, I want to look at y equals cosine x. So example, y equals cosine x. So of course the function that we're looking at here obviously takes the reals to the reals, and I know everybody knows what it looks like, and that's why I feel free to do a terrible job drawing it. Like so. Like so. Don't want to make it look like it ends there. Okay, if you pick a particular y, say y equals 1/2, then f inverse of 1/2 is a set of infinite size. So what is it? All the 60 degrees. So it's all the x's that have a cosine of 1/2, whatever the heck that is. So all the x's that have a cosine of 1/2, and there are infinitely many of them. So in fact, these parts here, this is capital P sub 1/2. These parts here can in fact be infinite sized. If I look at f inverse of square root of 3 over 2, that's all infinitely many. Capital P sub square root of 3 over 2. And so what we've done then is we've split all of the x's on the x-axis into these parts. The part that maps to 1/2, the part that maps to square root of 3 over 2, etc. Every one of these parts has infinitely many x's. And so in splitting this up into the different parts, we have created equivalence classes. These numbers are all the same in the sense that they all have the same cosine. They're not the same in that they have the same square. That's just not what we're thinking about at the moment. At the moment, we're thinking of them as the same because they have the same cosine. And these numbers are all the same in that they have the same cosine. So we have divided up the universe, the domain. We've divided up the universe into those things that can happen. The things that can happen is you could have cosine of x is 1/2. You could have cosine of x is square root of 3 over 2. You could have cosine of x is 0.90914. So those are all the things that can happen. So an equivalence class is one thing that can happen. And a partition, when you collect together all the equivalence classes, you've got all the things together that can possibly happen. Okay, all right, very good. So we'll stop there. Okay, bye-bye.